Today I will be presenting the paper entitled Framework for Dimensioning Battery Energy Storage Systems with Applied Multitasking Strategies and in Microgrids. My name is Athila Santos. I'm one of the authors, but I also have some of my colleagues here that contributed also for this work. This is a research paper, and the content for this presentation is as follows. So we start with the purpose. So what is the idea of the paper? Of this work, and then I will explain how we try to solve it using a funnel framework. I will characterize the case study that we use and showing the results, and later the sensitive analysis that we did on top of that. The central idea of the paper is to study battery energy storage systems that we'll be calling BESS, the acronym, to help on the feasibility, especially economically, of the microgrids. So the idea is to show how storage systems, especially batteries, can help on the economic feasibility of microgrids. So in order to make this more feasible, we come up with multitasking strategies. So not using only the battery energy storage systems for one purpose, but actually use them for different scenarios and bring more value for the entire system. Um, has a strong focus on microgrids, so using these storage systems for microgrids. And for that, we will use the funnel structure on a case study here in Denmark, island that we have called Aeroe, and also show how the sensitive analysis can interfere on the final availability of the system. First, we'll talk about the methodology that we use here. We developed a framework based on a funnel template. So the idea of this funnel template is to compress data from the top, more generic and general data into the bottom in a focal point. So filtering and studying and describing better the systems that we have. So from more general concept for more specific concept. The framework is also structured into three dependent stages. So the first one is called data acquisition. The second is system analysis, and later the optimization of the final system. Each one of the steps here will be discussed later on this presentation. For the multitasking strategies, there are several uh, strategies, but we focus here on three of them. So the first one, arbitrage. So basically is a time shifting strategy that focus basically on energy prices that compare peak hours with the off-peak hours and how this can affect the system. And using the energy storage systems, of course, in order to uh, balance the prices between these times. The load following is an idea of using storage system to balance generation and demand. So basically, see how much internal generation there is and how we can use the storage systems to balance with the local demand. And the last one is frequency regulation. So basically, how energy storage systems can help on frequency regulation. So for under frequency and over frequency situations. For our case study, so Aeroe, the microgrid in Denmark, so we analyze over a period of 1 year how the consumption and production behaves. We can see here by this graph is that the local production inside the microgrid is not enough to cover the consumption all the time. Okay, so if you see the green uh, area, so this is not higher than the consumption for several times during the year. So it's very clear that in order for the Euro microgrid to be more independent, it needs to have more resources. It needs to have more ways to balance these systems. And we believe that battery energy storage systems can help to achieve this idea. We also can see how the peak consumption behaves along the year. So we can see that we have most of the time some base load, and for a short period of time some peak loads that need to be covered. And this is quite detrimental for the overall system. And this can also be used in order to dimension the energy storage system. The next step is to study how the energy price can behave in the future. And for that, we took a 1 year energy price from 2019 and we extrapolate until 2040, actually using a study from the Danish DSO system in order to account for the variations of energy price during these periods, and also to account that for the design of the storage system inside the microgrid, to see the relevance and how much money we can save with that. So then we study how the net load and the accumulated deficits in a Aeroe system are distributed over some probability density graphs. So the idea here is to show that when we talk about capacity, we have as a mean value close to between 3 and 4 megawatts, and when we talk about energy, something with almost 50 megawatt hour. And we can use this information because we know the average, so we can use with some standard deviation to cover these areas below the probability density. In order to study our case, we need, of course, to select what is the best energy storage system. And here for the batteries, we analyze several technologies and their levelized cost of storage. And we can see here that the one that has best cost benefit is with the lithium, and this would be used in our case for all the simulations. To simulate our case study, we use a tool called Energypro, developed by EMD International. And the idea here is to use a modeling software that combine technical and economic optimization to study a variety of energy scenarios using different technologies, and we can also select some different storage systems here. These results would give us um, quite a wide range energy scenarios that we can use in order to compute the availability of our solution. So as a result of the simulation, now we can compare how the power capacity and storage capacity performs in the system using the net present value of this technology. Okay, so basically we can see that 5 megawatt of capacity and 42 megawatt hour is the first selection, the initial guess for the dimensioning of the battery storage system. So here we can see how the caps, OPEX, revenue, and net present value for the simulation case, and also how the stacked revenue is distributed between the three strategies that we analyze here. We can see that the frequency, the load following is the provides very little direct financial value to the system. So the reason for that is because there is a small difference between the cost of import relative to the income from exporting from the system. Um, on the other hand, the frequency response is the highest contribution task of the system, and that should be used with the higher priority for the evaluation. So when we compare two scenarios here, the base, so without the battery energy storage system, and with the battery energy storage system, we can see how the electricity import affects the overall result. So there is reduction of 38% of energy being imported by the system when we use battery energy storage systems. So this is the green curve here. And we are just analyzing the first 70 hours to have a more clear picture. The results of the load following test can also be visualized on the part B. Here we have three visualization, the production, so how much we are producing inside our in a typical day in our microgrid, the base load, so only the base load, so the load that needs to be consumed in average on the system, and also the battery energy storage system load. And what we are doing here is to try to move the load consumption on times there are more production. So we can see here that the curve yellow, the traced, the yellow curve is concentrated on this area that we have more production in the system. So we can benefit when we have higher production in the system. The shift increases the system ability to utilize the production in almost 26%. Now, if we see an example of how the load following behaves, we have three graphs here. The first one is the electricity consumption and production. So the consumption is the orange one here in the middle, and then the other curves has the different production inside the microgrid. We can also see the battery energy storage system energy when it's discharging and charging, the blue and the orange curve. And the last bottom curve shows the state of the storage level. So how much megawatt hour is stored inside our storage systems. By looking at the graphs, it can be seen that the battery charges, so the orange curves, when the system has excess of energy, and discharge if there is a deficit. So usually you have much more production on the charge areas than you have consumption in the system. So it's quite favorable for the load following strategy. We can also stack different strategies. So when we have load following together with the arbitrage task, so we can see how the system behaves. So the first curve here, we have the electricity spot price with the day ahead prices. In the middle, we have again the consumption and production inside the microgrid. And we also differentiate now the arbitrage discharge, so the green curves. And the bottom last curve is the state of charge of the battery storage system. We can see that when we have higher prices in the system, we have more discharge of the battery. So the storage systems are helping the system not to import energy when the price is too high. For the sensitive analysis, we would like also to study how the production, so how investment in production instead of only the battery energy storage system would affect the overall performance of the system. So here, for example, in the case of if we analyze the PV, we are considering how the size of the PVs 1 megawatt, 5 and 10 megawatts, they could interfere with the net present value. We can see here that for especially the battery energy storage system is quite beneficial for the net present value of the system. So we can even when we increase the solar production, if we combine that together with our battery energy storage system, we can have a much better result. We also like to study the subsidy effect of the system, so how subsidies can help in the system. Here we can see that the break-even point is when very close to to 40, 48, when we have 50, 55 crowns per megawatt hour. So when we analyze the net present value of the investigated subsidies added to the battery energy storage systems, we can see that we have a break-even point at this level. Okay, so if you have any questions, so now I will be here to try to solve them.